Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help us out over here, and it also helps us reach others in need of assistance with these topics. So what we're covering in today's video is we're going to be looking at structural analysis, and we're going to be finding some reactions for statically determinate beams. And this will be the fifth part in this series. So what we have going on here is that we have this large beam over here, and we are told that point E and F on this beam are hinges. So looking at this beam overall, we have two hinges right here and here. We also have a pin reaction here at A roller at B, another roller at C, and another roller at D. So if we didn't have these hinges, this beam would be statically indeterminate, meaning we cannot solve it by summing forces in the X direction, summing forces in the Y direction, or just summing moments and only using those three summation equations to find the reactions. But because there are hinges there, we can break this thing apart, because a hinge, all it does is it connects two members together. And a hinge can only transfer translational forces such as X and Y forces, your horizontal and your vertical forces, across it from one member to another. So for instance, hinge E can only transfer horizontal and vertical forces across this member on the left to this portion in the middle. Same thing with F. A hinge cannot transfer moment. A hinge allows for rotation. It does not resist any type of rotation. So think of a hinge in a beam like a hinge on a door. It allows the door to swing, but your door is not moving up and down, and it is not moving left to right. So whenever you have a hinge in your member, all you want to do is you want to split your member at the hinge locations. So depending on how many hinges you have, you're going to end up with multiple members. So we have a left side member from A to E, a middle member from E to F, and then a right side member from F to D. So essentially what we have here is this portion right here, another one right here, and another one right here, where this is A, E, E to F, and then F to D. So what we're going to do is we are going to treat each of these sections as their own little beams. Let me just throw on all our support conditions here. And at a hinge, we will also just treat that like a little support. So a hinge, as I said, can only resist or only transfer horizontal and vertical forces here, no moment. So it's kind of like it's a little pin reaction wherever it occurs. The one thing you have to watch out for with a hinge, though, is that since this is the same point on this segment and this segment, the left and the middle, let's say we get a reaction here for our middle segment of 3 kips in the upward direction once we solve for that. Well, this magnitude over here on this side has to match that because it's at the same point. But the arrow direction has to be in the opposite direction when you go to the other member. It's like looking in a mirror. It's the same reflection, just opposite locations. So whenever you're working with a hinge, keep that in mind, because that's a big mix-up and a thing that can obviously go wrong very quickly, is that you have to have the same amount of force at your location where you broke your hinge, but the arrow directions are in the opposite or the opposite direction at the opposite hinge point. So looking at our members here, oh, I did not mean to erase that. Looking at our members here and what we have going on up here. Remember, each hinge point you can treat like a pin. So there's going to be an unknown horizontal and an unknown vertical going on at each hinge location. So looking at the left side here, we have a pin, a roller, and a pin. Can we solve for anything using our 3 unknown equations here? Not really. But what about the right side? Same situation there. Too many Y forces going on. Too many. So look at the middle here. How many unknown Y forces do we have? Well, we would have our EY and our FY unknown. Well, there's only 2 there. So we can use our 2 equations of summing moments in the Y, or summing forces in the Y direction, and then summing moments about a point to get one of these reactions. Well, what about the horizontal forces there at E and F? Well, looking at the overall beam, do we have any horizontal forces being applied at all? No. Everything that's being applied is a vertical force. So we will have 0 horizontal forces inside our member. Well, really the only reaction point that has a horizontal reaction is here at A. So since there are no horizontal forces, everything is vertical, the horizontal reaction at A is automatically 0. Thus, every other single horizontal portion throughout here is going to be 0. So even though E and F are pins, their horizontal forces are going to be 0 as well. So that makes life so much easier that we don't have to worry about that at all. So looking at the middle one, this is all we have. We have 2 reactions and 2 unknowns here, EY and FY. Well, we can solve for that. So let's just go ahead and let's do this where we do our redrawing here. We have 8 kips, and when you're looking at your member, you only care about what's being applied to that member and the reaction points attached to that member. So I don't care about this 2 kips per foot or the 16 kips over here on this left side, and the same thing for the 3 kips per foot on the right side, because I'm only looking at the middle member here. So I'm going to assume my reactions at the hinges here in the upward direction, and you can see the distances up here. So just like any other, just treat it like any other beam reaction. So let's just go ahead and let's sum moments. And I'm just going to sum moments at E, and that will give me Fy at the start here. Pretty simple equation. Well, we would have our 8 kips of force. It's rotating clockwise, so that would be minus times its distance over to E, which is 9 feet. And then plus Fy rotating counterclockwise, and its total distance to E, which is 12 feet, equal to 0. Thus, my Fy would pop out to be 6 kips, count to be positive, so I know that upward direction is correct. Now, that is not a reaction. That is just my force in my hinge. So let's go ahead and let's go and get the EY reaction, which would be the force in the other hinge. And we can just sum forces vertically here. So taking up is positive. Once again, very easy equation. So we would have our minus 8 kips plus our 6 kips from Fy, and then I assumed E sub y upward. Well, E sub y is just going to pop out to be 2 kips, came out positive, so that upward direction is correct. So what I have going on here, if I go back to my little broken apart free body diagram here, I have 2 kips upward, and then I have 6 kips upward regarding the middle section. Well, now that I have EY and FY, I can go either to my left side or my right side in order to solve for the actual reactions of this member. Well, it doesn't matter which one you go to, but let's just work from the left side here. Well, I know that EY is 2 kips. It is upward on this segment. So on this section right here, it is still going to be 2 kips, but the arrow direction will be in the opposite direction. Remember, it's like a mirror. Same magnitude, same reflection, but everything is reversed. So we would have 2 kips going downward, and the same thing on this side, on the left side as well, with Fy. It would be going downward 6 kips. So essentially what I've done is I have replaced this support here with 2 kips of force. So now it just becomes a 2 support type beam, and I can solve for that pretty quickly. So let's try to fit it in up here. And let me do some deleting here, if it will let me. There we go. All right. So I'm going to try to write it in here for this left side of this beam. And let's just go ahead and do that blue. So looking at my left side of my beam, essentially what I have here is I have 2 kips going downward right here at E for this left side. So I would have a reaction at AY, I'm assuming upward, and a reaction at BY assumed upward. Remember, A sub x we already determined is 0. So let's go ahead and let's just sum forces at point A, and then we can get our reaction at B. So we would have our 2 kips per foot of uniform load multiplied by the distance that it runs, which is 12 feet. And then we need to find the distance from the center of that to point A, which is just a rectangle, and the center of the rectangle is just its distance over 2. So that would be 12 feet over 2, which gives me 6 feet. That will be rotating clockwise about point A, so it is negative. And B sub y I've assumed upward, so it's rotating counterclockwise, so it's positive. Its distance to point A is 12 feet. Then I'm going to have the 16 kips rotating clockwise, so it's negative. Its total distance is 20 feet to A. And then I'm going to include the 2 kips right here from point E right here. It will be going downward, so that is rotating clockwise. So it'd be minus 2 kips times its total distance to point A, which is 24 feet. And that is all you include. Remember, it's like you've just sliced your member right through here, and you're ignoring everything on the right side at the hinge. You only include what's on the one side of the hinge that you are looking at. So easy equation to solve here. By will just pop out to be 42.67 kips. Came out to be positive, so up is the correct direction. And there's one of my reactions. Alrighty. So since we have B sub y, let's just sum forces in the vertical direction, and then we can get A sub y. Well, we have A sub y assumed upward, so plus, minus off that uniform load of 2 kips per foot times the distance it runs, which is 12 feet, plus B sub y, which is 42.67 kips, minus off the 16 kips, and then minus off the 2 kips there from the hinge at E equal to 0. Well, A sub y is my only unknown in there, so just rearrange and solve for it. And you get A sub y is equal to a minus 0.67 kips. So the minus sign just indicates that I assumed the wrong direction. So A sub y is actually going downward 0.67 kips. And does that make sense? Well, let's look at it this way. We have 2 kips here. We have a massive 16 kips here. And then we have only 2 kips per foot right here. So what's happening here is that we have 18 kips on this cantilever, which is a pretty large cantilever. It's 8 feet and then an additional 4 feet there. So these forces with the 16 and 2 kips are enough to overpower the 2 kips per foot. And my beam is trying to rotate like this. So A sub y has to be going downward to bring that reaction back down. So yeah, it does make sense that it is going downward. Alrighty. So before you move on to the right segment, because the only reactions we have left are at C and are at D. So before we move on there, it is always good to double check your little section that you just worked with. So it's just like any other check that you would have for a beam. So since we summed moments at A, and then we just summed vertical forces to get A sub y, let's go ahead and let's check by summing moments at B before we move on and see that A sub y is the correct value. So summing moments at B, just using this left segment again, equal to 0, we would have our 0.67 kips for A sub y times its total distance to B, which is 12 feet. Since it is going downward, it is rotating counterclockwise, so it would be positive. And then plus the 2 kips per foot times the distance it runs, which is 12 feet, times the distance from its center to B, which would be 6 feet. And then we would have the 16 kips, which is rotating clockwise, so minus 16 times 8 feet, and then minus the 2 kips at E from the hinge times its distance to B, which is 12 feet. And does that equal 0? Yes, it does. So that means that we have the correct reactions on this left side of this hinge at E for AY and BY. So I'm just going to go ahead and write these in here, 0.67 kips, and then BY is 42.67. And then we also had F over here, which was 6 kips down for our right side of our segment, of course. All right, so let's go ahead and let's work on the right side of the segment, keeping in mind that we did find F on the center to be going upward 6 kips. So what that means is that on the right side of the segment, the FY will be going downward 6 kips. So as you can see right here, we had 6 kips upward on this segment. So that means on the opposite side of the hinge, which would be the right side of the hinge of F, that means it will be going down 6 kips. Remember, same magnitude, opposite direction on the opposite side of the hinge. So essentially what we have going on here is this right side from F to C to D. And I just need to determine what dy is. and I just need to determine what CY is, and I'm just going to assume both of those upward. Safe bet, right? Alrighty, so let's see what we have going on here. So let's sum moments about D, and then we can get C sub Y. Alrighty, so we are going to have the 6 kips per foot at F, or 6 kips per foot, 6 kips at F, rotating counterclockwise about D. So it'll be 6 kips times the total distance to D, which if you add the 12 plus the 3 plus the 9, gives us 24 feet. And then I have CY assumed upward, so it'd be minus rotation times its distance to D, which is 12 feet. And then the 3 kips per foot will be rotating counterclockwise about D, so it's 3 kips per foot times the distance it runs, which is 12 feet, times the distance from its center over to D, which would be 6 feet. And that's all I have there, equal to 0. When you rearrange and solve for C sub Y, it comes out to be exactly 30 kips. Came out to be a positive number. So that means my assumed arrow direction of upward was correct. Alrighty, so since we have C sub Y, let's take the easy route. And let's just sum forces in the vertical direction here for this right portion of this beam to get D sub Y. So we would have the minus 6 kips at point F, plus the 30 kips upward at C, and then minus off the 3 kips per foot times the distance it runs for that uniform load, and then plus D sub Y because we have assumed it upward. And our D sub Y is the only unknown there, and it pops out to be a positive 12 kips, which means the upward direction is the correct one. So C sub Y is 30, and D sub Y is 12 in the upward direction. And you may be asking, well, why was A sub Y downward and D sub Y is upward? Well, it's the same reasoning over here. So we only have 6 kips out here versus the other time when we had 18. This magnitude of the uniform load is 3 kips. This one is only 2. So there's more load on the back end of this beam here at D because it is trying to do this. It is trying to rotate like that, with the 6 kips pushing it down here at the cantilever, and then the 3 kips per foot trying to push it back downward. Well, this 3 kips per foot is enough to keep this beam looking something like this. So we would have the 6 kips pushing it down here, but the 3 kips is enough to bring this thing back to flush. That way it's still pushing down on point D. So point D has to be pushing backwards or in the upward direction to resist that 3 kips per foot. So yeah, it does make sense that D is going upward while A is going downward, because we don't have this massive 16 kips on the cantilever, and we have a larger uniform load. So we have found all our reactions here at A, Y, B, Y, C, Y, D, Y. Well, before we move on and do an overall check, let's just do our small check for the right side of the member. And we're going to do that exactly the same way as we did with the other portion on the left side, where we are going to sum moments at the other reaction we did not start with, which was C. So summing moments at joint C, we would have our 6 kips per foot, or 6 kips times the distance to point C, which is 12 kip. Oh my gosh. We would have 6 kips of force times the distance to point C, which is 12 feet. Rotating counterclockwise, so it is positive. And then we're going to subtract off the 3 kips per foot times the distance it runs, which is 12 feet, times the distance to point C, which is 6 feet, rotating clockwise about point C. And then lastly, we have point D, which is 12 kips, rotating counterclockwise about C, times its distance, which is 12 feet. And does that equal to 0? Yes, it does. So the right side of the segment, or the right side of this beam, is in equilibrium. So we have our reactions here, and you could stop here if you wanted to, but let's do an overall check to make sure that we have everything correct here. So what we're going to do is we're going to piece the entire member back together as shown in the picture here. And what we're going to do is we are just going to, because we can't really check moments, because the hinges don't allow moment to move across, but it does allow for the vertical portions to move across. So what we're going to do is we are going to check everything here together, and we're going to sum vertical forces here, because that's the only thing that we really have going on here. We have no X forces at all, and the hinges will only allow the vertical forces to move across, not moments. So our final check will involve our Y, not summing moments. So we're just going to have everything on here and see if it is in equilibrium. So we have AY going downward, so minus 0.67. And then we have the minus 2 kips per foot times the distance it runs, which is 12 feet. Then we have plus b sub y, which is 42.67. And then minus the 16. And then we do not include these reactions at the E or the F because they're automatically being transferred over. And then we would have minus the 8 kips. And then we would have plus c sub y, which is 30. And then we'd have minus the 3 kips per foot times the distance it runs, which is 12 feet. And then plus the 12 kips here for d sub y. And let's just double check to make sure we have everything in here. So we have minus a sub y, minus the uniform load, plus b sub y, minus the 16, minus the 8, plus c sub y, minus the other uniform load, and then plus d sub y. And does that come out to be 0? Yes, it does. So we have overall equilibrium with our individual sections when we take out the hinge and we separate it, and then we have overall equilibrium for the entire system. So these are my reactions, and let me just rewrite them real quick. We would have AY of 0.67 kips downward, B sub Y would be 42.67 kips in the upward direction, C sub Y is exactly 30 kips in the upward direction, and D sub Y is exactly 12 kips in the upward direction. And then, of course, AX was 0. So those would be your final answers for this problem. So no matter how many hinges you have in your problem, you treat them exactly the same, and you treat the overall problem exactly the same, where you would separate your member at the hinges and then treat those hinges like little pin reactions. And then you just have to pick which part of the members, in this particular case, the left, the middle, or the right, to start with and see what you can find, because the ultimate goal is to get to the reactions. But sometimes you have to start where your hinges are in order to find the hinges and then transfer that force across. So I hope this video was helpful. And if you want to see more problem solved this Friday, please check out the other videos on our channels. We're trying to upload daily. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all of that does help us out. Thank you for watching, and I hope you have a fantastic day.